There are two fundamentally different ways atomic nuclei can release enormous amounts of energy. One involves very heavy nuclei, elements like uranium. Those nuclei can split apart into smaller nuclei, releasing enormous amounts of energy in the process. That process is called fission. Fission is how the first generation of nuclear weapons worked, and it is also the process used in nuclear power plants today. Modern thermonuclear weapons also rely on fusion. In fact, they use an initial fission explosion to create the extraordinary temperatures and pressures needed to trigger fusion reactions. But stars work differently. Stars accomplish this naturally, through gravity. In fusion, the lightest nuclei, hydrogen, are forced together under extraordinary pressure and temperature. Those hydrogen nuclei combine to form heavier nuclei. And that process also releases enormous amounts of energy. For most of a star's life, that fusion energy pushes outward against the inward pull of gravity. And that balance is what keeps a star alive. In this episode, we are going to explore how stars produce that energy, how gravity and fusion remain in balance for millions or even billions of years, and what it really means when a star finally begins to run out of fuel. What you are looking at here is part of the Orion Nebula. This vast cloud of gas and dust is what astronomers call a stellar nursery, a region where new stars are actively forming. Over enormous periods of time, gravity slowly pulls parts of these clouds together. As the cloud collapses, pressure and temperature rise. Eventually, conditions at the center become extreme enough for fusion to begin, and a new star is born. Inside the core of a star, the pressure and temperature become enormous. Hydrogen nuclei are forced together so violently that they can overcome their natural electrical repulsion. When they fuse, they form a heavier nucleus. In the process, a small amount of mass is converted into energy. That energy pushes outward from the core and helps hold the star up against gravity. As gravity continues compressing the core of a massive star, the temperature rises even further. That allows the star to begin fusing heavier and heavier elements. Hydrogen becomes helium. Helium fusion produces still heavier nuclei. And over time, the star climbs a kind of fusion ladder, building progressively heavier elements deep within its core. For a long time, one of the great unanswered questions in astrophysics was this: if the universe began mostly with hydrogen and helium, where did all the heavier elements come from? The answer, scientists eventually realized, was that stars themselves were building those elements through fusion deep within their cores. When I was in high school, I attended a lecture series in Salt Lake City given by William Fowler. At the time, scientists were still working out many of the details of how stars create the elements. Fowler was one of the scientists helping solve that puzzle. His work helped demonstrate that stars are not simply producing light and heat. They are also forging many of the heavier elements found throughout the universe. Years later, Fowler would receive the Nobel Prize in Physics for that work. What I did not fully appreciate sitting in that lecture hall as a high school student was that the atoms making up planets, the Earth, and even life itself had once been created deep inside stars. But the very process that allows stars to create heavier elements also slowly changes the structure of the star itself. As heavier elements accumulate in the core, gravity continues compressing the star further. That rising pressure and temperature allow still heavier elements to fuse. And so the star continues climbing the fusion ladder. But this process has a limit. Eventually, the core of a massive star begins filling with iron, And iron changes everything. For millions of years, fusion allows a massive star to resist the crushing force of its own gravity. But once the core becomes dominated by iron, the star can no longer continue generating energy through fusion. Iron fusion consumes energy instead. In that moment, the balance that has held the star together its entire life fails almost instantly. The collapse of the core happens with astonishing speed. And once it begins, there is nothing we know of capable of stopping it. In the next episode, we will explore what happens when a massive star begins collapsing inward. So, come walk with me.